Okay, I guess I'm on. So before going into the full lecture, I'll just a little bit of history of zero-G. It was started by Peter Diamandis and Byron Lichtenberg, both of whom got their degrees here at MIT. I've known Peter for many years. I was with him in the summer of 1994. Yeah, 1994 at the International Space University, and he told me that he was planning to form this zero-G company. Well, one of my brothers is a real space nut, and all the time I was at NASA, he was bugging me, Jeff, you got to get me a ride on the zero-G plane. I said, no, NASA doesn't really do that. But so when Peter told me that, I said, oh, this is great. He was gonna, this was 94, he was gonna turn 50, my brother in 97. So I'll get him a ride for his 50th birthday. It took Peter 12 years to get FAA approval. But I ended up getting him a ride, my brother, for his 60th birthday. And he said it was worth. So first of all, just terminology. We have lots of different expressions, and including zero-G, which of course you all know, as Ariel said, doesn't really exist in that sense. But what I want to do, I think we can't really do this. We have rotating chairs and it's small. But what I would ask people to do, imagine you stand in a chair and you jump off, and while you're falling, you are zero-G. If you had a scale on your feet, okay. So the point, and excuse me if this seems very simple, but it's amazing that a lot of people don't quite get it. But let me ask people here, what causes weight? And we have different weights on different planets and so on. This is not a trick question.
Gravity. Yeah.
All right, so gravity. Now, you're standing on the table, you jump off, a scale is attached to the bottom of your feet. As soon as you leave the table, what's that scale going to read?
0.
Okay. Has gravity disappeared?
No.
So, and I'm, in a sense, yeah, sure, gravity pulls us towards the Earth, but that's not what creates weight. Newton's third law, for every action there's an equal and opposite reaction. Gravity is pulling you towards the Earth and the Earth is pushing back. So if you have a scale that's on the ground and you're standing on it, you're pushing in one direction because of gravity, the Earth is pushing back, and that's what gives you weight. And it's a simple concept. Once I've said it, I'm sure it's obvious to you, but the ironic thing is when you're in a state of free fall, falling from the table to the ground, gravity is still pulling on you. So here's the deal. If the only force that is acting on you is gravity, you are weightless. The other forces, the non-gravitational forces, are what give you weight. On the Earth, that's 1G, and there are other forces up in space, which we'll talk about later. And so, you've all, I don't know if any of you have actually tried to take a scale in an elevator. In some physics departments, they have this so that you can, when the elevator starts to accelerate up, your weight increases because it's you have the acceleration, which by general relativity is equivalent to gravity, right? And if it starts going down, your weight will slightly decrease and so on. So, okay, that's enough of that. But just remember the takeaway point. When the only force that's acting on you is gravity, you are weightless. So that's what we call free fall. So just a little background on ways that people have done experiments in weightlessness. You can have a drop tower. And actually, towers were used back in the early, like in Revolutionary War type days when they had lead shot. They would have, at the top of a tower, you'd have a bucket of molten lead. You'd pour that through a strainer with holes in it, so you'd get little droplets of molten lead falling. And if you've seen liquids in weightlessness, the surface tension makes them spherical. So during that fall, the lead drops would become spherical, then they'd fall into water, and you've got nice lead shot. And of course, there, they didn't evacuate the tower. For true free fall, obviously, if you have air resistance, then you're not going to have true free fall. That's why, you jump out of an airplane, eventually you reach terminal velocity. And so this big drop tower in Darmstadt, Germany, they evacuate it before they do experiments, and it's high enough so you can get about 4.5 seconds. And there are some experiments which can be done in a short time. And they even have a system where they can actually, using a big spring, they can push it up in the air. And so while you're going up, you're also in free fall. You're not falling, but gravity is the only force acting on you. So then you get 9 seconds. If you want longer times in free fall, that's what we're going to be doing here. You go to the airplane. If you want even longer times than that, this isn't done so much anymore now that we have a space station, but for several decades, they would have sounding rockets. Sometimes we used sounding rockets in, I did this with X-ray astronomy to take X-ray telescopes above the atmosphere, but there were also microgravity flights where you could get typically 5 or so minutes of good weightlessness, which is like the Blue Origin suborbital flights and so on that we do now. And then ultimately you go to the space station, and that's in orbit. So the space station, obviously you can do things for a long time, and you can repeat things, and there are a lot of advantages. You do have crew up there, you have a lot of machinery, and so we always talk about microgravity, and I want to give you an idea now of why we call it microgravity. So here is a frequency spectrum of disturbances on the space station. In other words, what are the forces acting, non-gravitational forces acting on the space station, which interfere with the, getting your real free fall. So, this is the frequency spectrum, and this is the amplitude. At the low frequencies, you have vents. The crew moves around, solar array rotation joint. The solar arrays are constantly following the sun. Ergonometers, that's the exercise bicycle, which they isolate as well as they can. And at the highest frequencies, we have the control moment gyros, which, they change their speed to move the station around. So, there are some experiments which don't really care that much about, very low levels of gravity. If you're growing a plant, it probably doesn't care if you have 10 to the minus 6 or 10 to the minus 5 G. But on the other hand, if you're growing crystals and you get little bits of disturbance, or you're doing a very sensitive physics experiment, this becomes important. So, what was developed for the space station was an active rack isolation system. You all know about the noise canceling headphones, right? They have microphones, they bring in the external sound, and then they invert that, and so they cancel out. And that's exactly what they do here. They have on certain racks, which are designated for very sensitive experiments, They have a sensitive accelerometer and then little piezoelectric actuators that essentially are 180 degrees out of phase with the sensed acceleration. And so you can see, doesn't do that much at the very highest frequency, but at the lower frequencies, it brings things way down. And if you notice 10 to the minus 6, so that's kind of where we're getting into the micro-G realm. Now this is, in electrical terms, these are AC, basically vibrational type of disturbances. There are DC elements as well, which limit the level of microgravity which you can attain. First of all, the space station has aerodynamic drag. This is a typical record of the height, and when we visit it with supply ships, we boost it, and then it comes down, we reboost it. Typically, a 1 Newton force on the space station produces, guess what? 2 micro-Gs of acceleration, and that's something that you've just got to live with. Now, in principle, I suppose they could put a 1 Newton electric engine on the station and get rid of that, but it's never been done. There's another thing that you have to consider, gravity gradient. Hopefully all the aeroastro people know about this. But an object in orbit follows a Keplerian orbit. In other words, for a given radius of your orbit, there's a certain velocity which you have to be in to stay in a stable orbit. If you have an extended object, that object is in an orbit which is appropriate for its center of mass or center of gravity. And so, look at the picture of the shuttle here. If the center of mass is here, now I'm going around the Earth. If I was up here, actually, by Keplerian law, I should be going slower, okay? But I'm not. I'm being pulled along by the structure, and that induces an acceleration, both from the difference in the G level, and also because assuming that you're rotating to stay in the same orientation like the space station does, you're rotating so you get centripetal forces. And we won't go through but at typical orbital altitudes, for every meter that you're off from the CG, you get about 2 micro-Gs, and then add that the centripetal is another 2 Gs. So again, all of these forces are in the nature of 10 to the minus 6G, and that's where we get the micro-G expression from. And frankly, on parabolic flight, I like to call it milli-G, because you're never going to, if you really need micro-G, you might be able to get it for a little while floating around, but anyway, the way they try to deal with that, the center of mass of the space station is kind of in the basic plane, and for experiments which are very sensitive to that, they try to put them in the middle of the labs rather than at the top or the bottom, just so that you minimize the gravity gradient. So, very briefly, I give several hours of lectures on these things, but weightlessness, you're floating around, your muscles aren't working, and so there's a problem with muscle deterioration, which is why the astronauts have to exercise a lot, cardiovascular fitness. Bones respond to stress. We walk around all the time, our feet are hitting the ground, the stress is transmitted through our bones, and they respond by putting enough calcium in to keep the bones as strong as they need to be. If you don't stress your bones, the body isn't going to waste that weight and calcium, and your bones start to lose calcium. The calcium in your bones is continually being recycled, and it's a question of how quickly you replace the calcium that's removed. this is being dealt with. Now, you can't just take calcium supplements. It'll just come out in your urine, and ultimately that increases the risk of kidney stones. But by doing stress exercise, lifting weights, for instance, it will help you. And you can't just lift weights in space. I mean, it's very easy, very nice. But so NASA worked a long time to get the advanced resistive exercise device, which people are coming back now with more muscle. Some of them, the ones who exercise a lot, with minimal bone loss, more muscle mass than they went to, but they're spending 2 to 3 hours in the gym. And most of us on the ground don't do that. Circulatory system, this is something you'll experience. We here on the ground, our body is in a homeostasis where everything is kind of balanced. You might wonder, why blood doesn't just accumulate in your toes. Our legs, the veins in our legs have a system of one-way valves so that every time you squeeze your legs and move them, the blood is pushed up towards the top. And that system continues to work even when you're weightless. And so the first thing you're likely to experience, a lot of people say that when they first become weightless, it feels a little bit like you're hanging upside down because you get this rush of fluid into your head, and that's what we're showing here. So initially, your legs lose blood volume, and we've measured the volume of your legs depending on your physiology. You can lose from 10 to 25% of your leg volume. Your heart initially expands. You have that extra fluid in your brain. We have in our carotid arteries and around your aorta, we have pressure sensors in the arterial system. They sense a higher pressure, and they don't know you're in space, okay? So they're saying, oh gosh, I've got too much fluid in my body. And so what happens over the first few days, you don't feel very thirsty, but you have to pee a lot, and you lose about typically 1 to 2 liters of fluid until you reach a zero-G homeostasis where your heart is actually slightly smaller than it was back on Earth. Your head is still a little bit inflated, but not nearly like it was the first few days. And that's fine until you come back to Earth. Because then all of a sudden, the gravity pulls the blood back into your legs, and lo and behold, you don't have enough blood in your head. And the early astronauts, and this was even up to the early shuttle flights. So anyway, they would do stand tests, and typically after a minute or two, astronauts would, basically they couldn't stand, they'd get lightheaded, and basically in order to prevent them from fainting, they'd have to sit down or lie down again. And that's why before coming back to Earth, we drink about 1 to 2 liters of saline solution to build back that fluid volume. Anyway, I'm not going to spend much time on physiology because you're all going to be designing various experiments, so I thought I'd finish up by, let's see, what circulatory system. Oh, there was one, this is a good time to do my experiment, I think, because, again, it will illustrate something about what happens in your body, but also something that happens in a lot of experiments, particularly anything that's going to have to do with fluids. And so for this, I love this experiment. Okay. So I've got a bottle here, and there's a little hole. Let me find the hole. Yeah, I put a little hole in it, okay? And so what I'm going to do...
Do you want to unplug the mic?
I think, well, usually when I do the experiment, I stand on the table, but I think I'll hit my head if I do. So I'm just going to hold it up there. We'll have to get some paper towels later. But, okay, so, I better take the top off here. It's much more fun when I can stand on the table. It looks very impressive, but, well, okay, so, You better watch out. Okay? Now, the reason that's coming out, hydrostatic pressure is caused by the weight of the water above it, okay? So this has weight because gravity is pulling down, and what's the non-gravitational force? My hand, I'm holding on to it. So now I'm going to let go, and I want you to watch. 3, 2, 1. Oh no, I missed the wastebasket. I'll try that again. Okay, could you see when it started to drop? We'll have to clean this up later. Sorry about that. I love that experiment. But that's what's happening inside your whole body when you go weightless. And it affects the behavior of all liquids. So something to consider. So I'll go through this fairly quickly. But there's lots of physical phenomena as well as biological phenomena that are affected when you change the gravity. And we'll look at a little detail into those. Combustion, fluids we've talked about, and we'll go through. You can read that faster than I can talk about it. So, combustion. First of all, the whole idea of convection. What causes convection? Why does hot air rise? It's not a trick question.
Because of Pivner?
What?
Because of Pivner? Because of the temperature?
Well, it's hot. Yeah, it's hot. It has a temperature. But why does hot air rise?
Because it creates a pressure differential.
Pressure differential? Hot air balloon. Yeah. You fill a balloon with hot air. Hot air is less dense, and so it weighs less than the cold air. So the cold air rushes in underneath and pushes up the hot air. Why does a bubble float up? You blow bubbles in the water, and the air bubble is lighter, so the water is heavier and rushes under. But when you're in weightlessness, hot air weighs exactly the same as cold air, which is 0. And so here's the deal. On Earth, on the left-hand side, you heat the bottom of a apparatus and bubbles form, and the bubbles come up, and you boil your water. We do that all the time. In weightlessness, it's very different. The bubbles don't go up to the surface. They just stay there, and they get bigger and bigger, and eventually you can see pretty much the whole bottom is covered with gas, and now you no longer get good heat transfer. This is why in Apollo 13, right before the explosion, the command went up, please stir the tank, because they had liquid oxygen, and they have a heater to heat the liquid oxygen, but you don't want just oxygen bubble to form around the heater, so you want to stir it around, and that's where they had the short circuit and so on. So no convection, no density-driven convection. There are second-order types of convection, like Marangoni convection, which is driven by surface tension. And actually, there have been a lot of experiments that have done to study these second-order effects, which, by and large, here on Earth, are masked by the first-order effects. And the same thing is true in combustion, because in combustion, I mean, this is what everybody knows what a flame looks like. It goes up, and the reason is the hot air is driven by density-driven convection. You take away density-driven convection, and you go from 1G to 0G, and things burn very differently. We did. I don't have a video of it. I should actually add that to this for another talk. But we did some combustion experiments on my last space flight. And we did one where we had a stream of air coming in this direction, and we lit we had a kind of a linear piece of paper that would burn, and we lit the paper in the middle, and you'd expect the air is going in this direction, so the flame would propagate in this direction. But because there was no convection and it was a fairly slow flow, basically the flame ate up all the oxygen, and so it had to, the only way it could propagate was to move into the wind where it got new oxygen. So it was totally counterintuitive, and this is very interesting. You know, we've done a lot of combustion experiments also for smoldering, for fire safety on spacecrafts, as well as there's a lot of other phenomena that go on in a flame. There's diffusion and chemical reactions, but they're overshadowed by this density-driven convection, and so there's been a lot of interest in studying combustion in weightlessness so that you can look at these second-order effects. Also been a lot of work since the early days of the shuttle program on growing crystals in space of various types for semiconductors, for biological use, protein crystals. When a liquid crystallizes, it gives off, you know, when water freezes, it gives off the latent heat of freezing. And so you're giving off heat, and that causes density-driven convection. And the idea is that in weightlessness, you get rid of that. And so we've had a lot of crystal growing experiments on the shuttle and the space station. And for some, but not all materials, and it turns out to be a lot more complicated, but in many cases, they've been able to grow larger crystals with fewer imperfections. For the pharmaceutical industry, that turned out to be interesting because they can crystallize proteins, analyze the proteins back on Earth by X-ray diffraction to get the protein structure, and that could be very useful in developing antibodies and all sorts of stuff. This is something I just came across a while ago, and I don't know too much about it, but it was quite fascinating, and I haven't been able to find out a whole lot more, but zero-attenuation fiber optics, somehow when they grow the glass, and it has to be done at 0.216 G in order to get the right crystalline structure. And again, I don't know that much about it, but the idea, if this really works out, and they're still doing experiments on it, fiber optics, you know, they need amplifiers periodically and power sources. And if you truly could have a zero-attenuation fiber optics, the economics would be fantastic. It's not 0G, but remember, we can create altered gravity here on Earth in a centrifuge, but you can only increase gravity. You can't, you know, people would ask us sometimes that when they visit NASA, where's your zero gravity room? You know, because they see these pictures of people floating. But you put a centrifuge in the space station, or on the moon for that matter, and you could create 0.216 G. So, as I say, I'm going to try to learn more about it because it's quite fascinating. Bioreactors, used in a lot of laboratories on Earth. Think of it as like a three-dimensional petri dish. So you grow an organic growth of some kind of tissue, you feed it with nutrients, and it gets bigger and bigger. It's going to want to settle out, so you spin the bioreactor, and that keeps it floating, basically. But at some point, if it gets too big and you have to rotate it too fast, then you're going to just disrupt the structure just because of the rotation. And so the idea of using these bioreactors in space, they've done them on Mir. We had one on the shuttle. I think they're putting one, I don't know why they didn't have one at the very beginning on the space station, but there's a lot of things. They've even gotten to the point where they've been able to develop a tissue to the point where it starts to vascularize, and so a lot of research opportunities. Telling time in space. Typically, the most accurate clocks we have here on Earth have been the rubidium fountain clocks, where you basically shoot the rubidium atoms up, and you excite them with microwave, and you basically can get the frequency that way. And the longer that you can observe, the more accurate you can measure the frequency, and that corresponds into the accuracy with which you can tell time. But you're limited by the amount of time that the atoms spend up at the top of the fountain, because then they fall back down. And so NASA now has an experiment on the space station, this deep space atomic clock. And again, I won't go into the technical details, but that was putting the whole thing together. Excuse me, this is in a satellite. It's not in the space station. They were going to put one on the space station, but this is in a separate satellite. And so the idea is you can increase the precision of timekeeping by at least an order and maybe 2 orders of magnitude. And remember that every time in human history that we have increased our ability to accurately tell time, it's led to huge technological advances. Our whole industrial civilization has depended on that. And the last big step with the portable atomic clocks led to GPS. And so who knows, another order or 2 orders of magnitude, what that will lead to. But you can do it because of the zero-gravity environment. And now we've developed 3D printing in space. And of course, a lot of these were tested first on parabolic flights, which whenever you can test something in a parabolic flight before sending it up to the station or putting it in a satellite, I mean, it's a lot less expensive, and very often you find things that are useful. So, some of you may want to think in terms of what you are going to propose as a prototype to test a certain technology or test an idea that ultimately could benefit from longer exposure to microgravity, in which case you propose something for the International Space Station. And then finally, up there, once you can 3D print things, we have the potential of actually producing large structures, which would be huge, because everything we launch now has to tolerate launch loads. You could imagine a gossamer structure up there, huge, and if you can build it in 0G, and you don't have to design it to withstand launch loads, there's all sorts of options. And I'm sure that in your lifetimes we're going to be doing these, and maybe sooner than that, maybe even in my lifetime, who knows. So this is kind of a summary. You can read it through. That's just of what we've dealt with. And I want to finish up just with some fun, a recording of a parabolic flight, which very long parabola. And in case you want to, anyway, good fun. Don't try this at home. And that's it.